Hello students, welcome back. We completed parts A and part B of exercise 2.4. Now part C is in completely different league. And do you remember this in number theory? What is phi of n? It's the number of positive integers less than or equal to n that are relatively prime to n. It's called Euler function, Euler Totient function, or Euler phi function. And it is very, very important in number theory. It's important in abstract algebra too. Anyway, that's what you have to prove. And I remember this from number theory, but I'm not so sure whether I used to prove it in number theory or not. It's been such a long time since I taught number theory, so I don't remember exactly. But let's do it here. Okay, let's begin. We have to do it in several steps, and step 1 is a reduction. Let's begin with Zm, and we're going to utilize part A and part B. Select any element from Zm, say R bar, then you can form a cyclic subgroup generated by that element, R bar. And if you apply Lagrange theorem, then that order must divide M, the order of the group. And of course, this order is unique. Consequently, we can decompose Cm like this. Union of these sets, and each of those sets share the same element, share the element with the same order, D. And of course, that D must divide M. So take the union of all those, and then we have to have disjoint union because the order is unique for each R bar. Now, how does that help? Let's take the cardinality, and if you take the cardinality of the left-hand side, then the cardinality of Zm is M, and in the right-hand side, we have disjoint union, so we have summation of the cardinality of the set here. And let me highlight this cardinality of the set in the right hand side in blue, and I claim that's phi of D. That's what we have to prove. So step 1 is this reduction, and we use part A and part B, especially part A as a matter of fact. And then we ended up with this. Some change of viewpoint. This decomposition here is a interesting technique. Okay, and then let's go to step 2. We have to prove that this blue is phi of D. So we must prove that the number of elements of Zm of order D is phi of D, the number of positive integers less than or equal to D that are relatively prime to D. Okay, we used to highlight this one in blue, and then that in blue. Now let's go back to part B of the problem. Zm has one and only one subgroup of order D. We are dealing with a subgroups of order D, so let's consider that. So if R bar in Zm has order D, and there's one and only one subgroup of order D, so it's got to be a member of this. So R bar should be one of this. So R bar should be one of those S M over D. If you don't like M over D form, you can use Q form as we did before in part A and part B, where Q is the M over D. But here I didn't want to introduce you with too many characters. So Q bar is your Q, 1Q, and we have 2D minus 1Q bar, all those. The same thing. M over D is Q, that's the integer. An alternative form may be more useful, however. Why? Because Euler Totient function is used for positive integers and less than or equal to, in this case, d, not like this, greater than or equal to 0 and less than d. Can I change that into strictly greater than 0 and less than or equal to d? Positive integer less than or equal to d. Can I do that? Yes, I can do that. Let's make this observation. This one here, which I just highlighted in green, and this one here, highlighted in green, are the same. D over d is 1, so that's 0. I mean, that's 1 times m, but m is congruent to 0 modulo m. Otherwise, they're all the same. And then also I made a little bit of change as well, moving m to the right. So this expression here versus that expression here, I don't think you're going to see any kind of trouble seeing these two are the same. And the reason I did it is to note that not all these will generate everything. Only when s over d, this fraction is in the lowest terms, will have a generator. That's my claim. That's why I emphasize s over d here. We're going to revert back to the previous expression, Sm over d, later on. So if this is in lowest terms, in other words, GCD, the greatest common divisor of d and s is 1, if they are relatively prime, then that fraction will generate all these, but otherwise it won't. In an extreme case, if you start from 0, I don't get anything. It generates only 0, just the identity. And 0 generates just itself, so the order is 1, and 1 divides d, and yeah, that's okay. And if there are some other fractions that does not generate entire subgroup here of order d, it'll generate a subgroup of that has order less than d, but it has to be a divisor of d because of Lagrange theorem, you see. What I claim here is I would like to get that phi of d, which is associated to greatest common divisor being 1, relatively prime. So what I claim is this Sm over d generates the entire subgroup if and only if d and s are relatively prime, or equivalently speaking, the fraction s over d is in the lowest terms, as I emphasize here. If I prove that, then I'm going to get this blue, and that'll complete the problem. And that's something we are going to do in step 3. So we must prove that this Sm over d bar has order d if and only if d and s are relatively prime. GCD of d and s is 1. Okay. If GCD is greater than 1, in that case what? GCD is say C, then we can manipulate like this. And let me expand the font so that you can read better. Sm over d, yes, m over d is an integer, so that's an integer. And then divide by c. S is divisible by c, d is divisible by c, so we have this kind of expression. And you may look a lot of fractions here, but that's an integer. All these are integers, actually. And then let's do this. Multiply by denominator d over c, which is an integer. Yes, c is a common divisor of d and s, so that's an integer. Multiply by integer to that, and then denominator cancel out. We have s over c times m, and s over c is an integer as well because c is GCD of d and s, so c is a common divisor of s. C divides s, so that's an integer. So integer times m, that's congruent to 0 modulo m. If you don't like modulo expression, you can just use bar expression. I usually prefer bar expressions. So this Sm over d bar times some integer is 0. So what do you get? The order of this Sm over d bar is that integer d over c or less, strictly less than d. You see, this one repeatedly added d over c times is 0, so the order has to be d over c or less, strictly less than d. So we got one of those. It does not have d, it has order less than d if GCD is greater than 1. Now, if GCD is 1, in that case, we have to prove that the order is indeed d. Let's begin with linear combination expression. US plus VD is equal to 1, where U and V are integers, and then here multiply by m over d. So multiply by m over d times 1. Let me expand the font. So m over d times 1, and then US times m over d, VD times m over d, yeah, here and there, and then manipulate U times Sm over d, V times m, and V times m is congruent to 0 modulo m. So what do you have? M over d is some integer U times Sm over d modulo m. And if you use the bar notation, m over d bar is integer times Sm over d bar. So the generator of this subgroup here belongs to the right-hand side subgroup. So this entire subgroup is a subgroup of the right-hand side subgroup. That's what I got. But then again, oh, I need this bigger font again. The right-hand side subgroup is S times this one here. So we have the other inclusion as well. So they have to be equal to each other. And then the order is D. You see, we studied this cyclic subgroup generated by m over d bar or q bar. So that has order D. That is the unique subgroup that has order D. So yes, oops, excuse me. Yes, if GCD is 1, then Sm over d bar has order D. We got it. And do you see that we completed the proof? In case you don't see it, let's backtrace. From step 3, we established this. So Sm over d bar has order D if and only if GCD of D and S is 1. And apply this to step 2. And what is this? Sm over D. That's arbitrary R bar, as a matter of fact. Arbitrary R bar can be written like this. And so arbitrary bar has order D if and only if this R bar is Sm over D bar, where GCD is 1. So how many R bars are there? That's the same as how many Sm over D bars are there, such that GCD is 1. Therefore, we can do this kind of counting. How did I lose this alignment? Okay, the alignment is back. So the cardinality, this R bar has order D, can be rewritten as R bar as Sm over D bar, and that has order D. And that can be rewritten as Sm over D bar, which is the same as R bar. And GCD is 1. And then, okay, this is not the same set, but the same cardinality. Just look at what kind of S values can you get. 1 through D, where GCD is 1. Remember, instead of 0 through D minus 1, I did 1 through D for convenience. And then that's precisely phi of D. Euler Totient function. If I apply this to step 1, I get the desired result. M is the order of Zm, which can be rewritten like this, sum of this cardinality, and that cardinality which I just established as phi of D, and that completes the proof.